Hey everybody, so welcome to our first CHUG meeting of the 2022 season. I'm Mike Siegel, one of the founders and organizers. Along with me is Steve Wampler, another organizer, and some of our guests. Our speaker today is going to be Alex Merced from Dremio, and we're talking about Apache Iceberg. Before we start, just a quick house note. We hope everything goes well with this. This is our first time using Zoom. We look forward to doing this in the future. If you have ideas for topics, please let us know. If you have ideas that you want to speak on, if you get a speaker, let us know as well. And at the same time, hopefully as the COVID releases and we have more people coming back to work downtown, we may be able to do live meetups and to do both Zoom and live meetups. So please, feel free to join. Also, we have a Slack presence, and if you're not on that, please contact me through the meetup website, and I will get an invite to you as soon as possible. Enough of those housekeeping things. Again, I want to welcome Alex Merced from Dremio. Alex, if you want to share the screen and take charge, it's all you.
Sounds good. Let's begin. Hey, everybody. My name is Alex Merced. I'm a developer advocate here at Dremio. And today we're going to be doing a talk on Apache Iceberg, an architectural look under the covers. So this is going to be more sort of an introductory of like what is Iceberg talk. Again, my name is Alex Merced. My Twitter handle is @AMDataLakehouse. If you'd like to follow me on Twitter, constantly putting out a lot of Iceberg content on migration, on different features of Iceberg, and so forth. So let's begin. Okay, so in this talk, what we're going to be talking about is what's a table format, okay? Because Apache Iceberg is a table format. So first thing we need to do is understand what is a table format and why do we need a new one? Why should we move on from the tools that we've been using before, like Hive tables? Now, how does an Iceberg table work? So the architecture of an Iceberg table. So what does it mean to have a metadata file and a manifest file and a manifest list? What are these things? How do they work? How do they relate to each other to make all these features possible? And then what's happening under the cover? So we're going to be doing some like practice queries or just showing you like, hey, if you do this query, what sort of is the path that Iceberg will take to make it happen? And we'll conclude with sort of what are the benefits? So yes, we understand how Iceberg works, but what is sort of, how does this really take us to a new sort of transformational place? So let's continue from there. So first thing we're going to ask ourselves is what is a table format? And bottom line is this. Imagine you have your data lake and you have all these Parquet files on your data lake, all these ORC files on your data lake, all these Avro files on your data lake. And at the end of the day, really like this 1,000 Parquet files over here, they really represent one unified data set. And it would be really easy for me when I'm writing my Python scripts or I'm writing my SQL queries if I can recognize them as a single data set, a table. And so that's what the table format is going to do for us. It's going to allow us to take all those files that are all along our data lake and say, these files right here, this is table 1. These files over here are table 2. Okay. Now, sort of the traditional old way of doing it, the Hive table way of doing it, was by basically saying, this directory here is my table. So this directory here, table 1, and the files inside of it are table 1. And essentially, we would use and follow that path. And that was transformational. That allowed us to, write SQL and have that transformed into map reduce jobs and make our lives easier when that was a thing. But bottom line is everything was still organized in directories, and that had some benefits and it had some drawbacks. But it is basically the standard, which is one of its biggest pros because sort of that Hive table standard format is the de facto standard. It works with pretty much every tool, every engine supports Hive. There's definitely a lot to be said for that. Okay, it supported things like partitioning. So you're able to create like a partitioning column, say, hey, I got this timestamp column. Let me create a partitioning column that represents a month, a date, or a year, and say, hey, let's partition based on that value. And this allows you to run queries that are much more performant because you can have, instead of doing a full table scan, you can just query that partition data. It was file format agnostic. You can use Avro files, you can use ORC files, you can use Parquet files. All that matters is basically where those files are located. You can atomically update a whole partition because basically what's going to do is just going to rewrite the partition. So basically you can make that update and have those sort of atomicity guarantees. And it basically, more than anything, it provides that answer to the question of what is a table. Allowed us to kind of create that sort of standard unit so that way we have sort of one definition of the data that can be used across different teams or different tools, instead of everyone trying to redefine what is the data set. But because we're looking at the data set as like a directory of files instead of sort of like a canonical list of files, smaller updates were a little bit harder to do. Okay, you want to update just one record in a particular partition, you're pretty much doing a rewrite of the partition under the hood. So that could end up being really inefficient and real time, really time consuming. Also, the safety of it. Okay, when you're trying to update multiple partitions or have multiple people with multiple jobs make updates, it becomes really hard to do that safely and really have those ACID guarantees to make sure we don't run into any problems with isolation or durability and so forth. Okay, and basically all these different directories, when you have like a lot of partitions, okay, it can, and all these different files in those partitions, having all those file operations can really end up taking a long time to kind of run these queries. And when it came to partitioning, because you created like a partitioning column based on, let's say, a timestamp column, people who are querying the table have to be kind of aware of that. So even though I may know, hey, I have this timestamp column, if I just query based on that timestamp column, I may not take advantage of the partitioning because the partitioning is really done on the column that was created from that column, the month, the day, the date column. So in that case, you could accidentally run into some full table scans if you're not careful with your queries. And the statistics were stale because you'd have to go out and do these reads to get your table statistics. That would take a long time because you're doing a full read of the table to get those statistics. And basically, all these cons are going to be things that like Iceberg is going to end up improving upon as we go forward. So as you can see, like we need a new table format because there are things that just aren't provided by that Hive standard. Again, still very used quite predominantly. Still, every tool supports it. But if we can turn those cons and turn them to things that are fixed, I mean, that would be quite transformational. And one day at Netflix, well, that question kind of came up. It was like, hey, we needed to kind of create something better. We need to be able to have tables that have correctness and consistency. We need faster query planning and execution. You'll see some examples later on where you go from waiting days for a query on a small bit of data to being able to query larger amounts of data in minutes. Okay, we don't want our consumers to have to really worry about like, okay, which is the partition column? Make sure I include that query, even though I'm already querying the partition column. So that way you don't have these accidental full table scans, and it's just easier to have more consumers up and running with the data. Okay, so the new way was to look at the data not as directories of files and say, hey, this table is this directory. Instead, say this list of files is the table. Okay, and that's going to allow you to kind of move in a very, very different direction, as you'll see, because we'll avoid a lot of these downsides and have a lot more flexibility in how we organize these files and how we track the table. But to be clear, Iceberg isn't a storage engine. It's not what actually stores the data. So you'd still be using something like an S3 to store the data. It's not an execution engine. Okay, you'd still maybe use something like Dremio Sonar or Spark or Presto, one of those kinds of tools to actually run the queries. It's not a service. Okay, it's a table format specification. It's a standard way of sort of setting up the files, collecting the data on the tables, and a set of APIs and libraries. So there's several like different Java and Python libraries that can then be used in order to incorporate these features into the execution engines, to build upon the different storage engines of the world, and basically to build that support for external tooling and working with tables that meet the specification. So basically Iceberg is the how-to, but at the end of the day, like how the actual storage of the data, the actual running of the transactions, that's all going to be done by external tools that choose to implement these APIs and these libraries. And so this picture right here is essentially the standard setup of like sort of what does an Iceberg table look like under the hood, which is really going to be what illuminates how it makes all these magical things happen. So what we're going to do is we're going to just kind of take a look at what happens when you do like a standard read, like you decide to select all or something like that. Okay. So essentially everything starts with the Iceberg catalog. Okay, so the idea basically here is that the Iceberg catalog has to be something that can provide an ACID guarantee. So this could be like a relational database, it could be a Hive metastore, it could be AWS Glue, You could use HDFS. You can use Nessie, which is actually a catalog store pretty much made for Iceberg, that creates like Git-like features. It's really cool. But basically what it does is that it's going to track really one main piece of data. It's basically a pointer to the newest metadata file. Okay, so that's going to be how we kind of reach that atomicity, because every time there's going to be a write, an update to the table, a new metadata file representing the state of the table at that point is going to get created, and this catalog will always point to the newest metadata file. So we'll always know what the current state of the table is, because that record in the catalog was always pointing to the newest metadata file. So that's kind of how we keep track of sort of like, what is the current state of the table? Okay. And also we can take advantage of a lot of the features like locks and things like that in the actual catalog to provide that atomicity to writes on the Iceberg table. Okay. Now, basically, once we get that pointer, it'll point us to the metadata file. Now, the metadata file, think of it as sort of like the table-wide definition. Basically, what this does is describing the table at the highest level. So it's basically giving you like a table ID. It's going to tell you what the current snapshot is. So we have a snapshot of the table at different states. It tells you what the current snapshot is and where the previous snapshots are. So basically, you have an array of snapshots. You'll have an array of partitioning schemes. So you'll know what the current partitioning scheme for the table is and what previous partitioning schemes are, because with Iceberg, you can do what's called partition evolution. So you don't have to rewrite the whole table if you want to change the partition. You'll be able to like just change it as you need, as you go, which is really cool. You can do schema evolution. So in this metadata file, it'll actually track the different schemas the tables had at different points. So that way, if you want to add a column or rename a column or change a column's type, you can do that. And it's all tracked in this at this high level. Okay. Now, what's going to happen is that let's say I'm looking at the newest state of the table. It's going to take a look at the current snapshot and get the current snapshot ID. And that current snapshot ID is going to have a path to what's called a manifest list. Okay, so while the metadata file is sort of like a global, here's all the information on the table at the highest level, past and previous, the manifest list represents the snapshot, a particular state of the table. So we're saying, hey, we want to look at the newest snapshot. The metadata file points us to where the newest snapshot is. That's the manifest list. And that takes us to our next step. So the manifest list, basically, all it focuses on is the table at a particular point in time. And basically what it does, it's going to have a list of manifest files. And each manifest file is a list of the actual individual data files. So basically what it does is that it's going to say, okay, hey, for this particular snapshot, to get the data that's currently part of the table at this point in time, these are the different manifests you want to look at. And then there's going to be a bunch of metadata, like basically stuff about different particular columns, partitioning and whatnot. And the thing is that the query engine at this point in time can now begin eliminating files it may not need, because depending on how the table is partitioned, it can actually take a look at this manifest list and start saying, well, this particular manifest covers this partition. That's not what we're looking for. Let's get rid of it. So now we're already starting to get rid of many of these files that we're not going to need to look at. We're not going to need to scan through. So we're already starting to trim down the amount of individual files we need to look at to speed up that query. But once it does that, it's going to eliminate as many of those manifests as it can and figure out, okay, these are the manifests that I do need to look at. These are the actual groups of files I do need to look at to do this query. It then starts looking at those individual manifest files. Okay. And see, like what's happening is you're having these layers of metadata that allow different layers of pruning. So that way you can prune chunks of files, and now we're going to start pruning individual files, which allows us to really kind of shorten down the amount of files we need to scan quite a bit, quite quickly. So then we get down to these manifest files, which are going to again list like the partitioning, the min and max of like each column for that data file. So that way it can be like, well, hey, you're querying by this particular column, and you say, hey, you only want things that are under a value of 10. By looking at the min max values of the data in each different data file, it can be like, okay, hey, we don't need this file, we don't need this file, we don't need this file, and just continue trimming down. And at this point, no data file has actually been scanned yet. Okay, this is just the planning part. It's just reducing the number of files it has to look at. And once it's done that, it's gone through all the manifest files that are part of that snapshot and sort of narrow down which files it needs to look at. It then will actually go and then scan those files and come back with query results. But that's sort of that path is going to be how it provides the speed that Iceberg does. And we'll show you an example so you can see sort of like the types of gains that you can see. Okay, so now what to do is we'll just run through some queries with a new Iceberg table so you can see like, hey, if we create a table, what happens? And get a feel for how these metadata files get created. Because at the end of the day, it's all about this layer, this tree of metadata. And that's what really makes it so unique, because a lot of those files can be reused. So different snapshots can reuse the manifests, and different manifests can reuse the data files. So that way you can actually maintain like that catalog of the table at different points in time. So you can like do time travel, things like that. So here what we're going to do is we're going to create a table. So here we're creating a table. Here's the table schema. We're going to put this using Iceberg clause because that's going to be what tells Spark that, hey, we're using Iceberg. So make the table using the Iceberg API. And we're going to partition it. And now look at the way we partition this. So instead of just saying, hey, this is the partition table, in Iceberg, you're actually allowed to express a transform. And this is going to enable a really cool feature later on called hidden partitioning. So instead of having to say, hey, let's create this other column that's the hour, okay, that we use the partition by hour, what we can do is we can just say, hey, here's our timestamp column. We'd like to partition by that column, but by hour. So it'll partition it by hour, but it'll still be partitioning that column. You don't have to make a second column. So someone querying the table won't have to make like an additional clause. So that whole issue of having accidental full table scans won't be an issue. Someone specifies a timestamp that basically Iceberg will know, okay, hey, I need to use the partitioning that exists. And that's super cool. Okay, so what's going to happen here is we create this new table. So what's going to happen is that we then register the new table with the catalog. We create the metadata file, and that's all that's created because the metadata file represents the current state of the table, and there's not really a snapshot because no data has been written to the table yet. So really, it's just a metadata file that says there's a table. Okay, and then and basically the underlying files. So basically, what will happen is you'll have a folder. So you still have directories, a directory called table1, and that's going to split up into two folders, metadata and data. All the metadata is in the metadata directory. All the data files are going to be in the data directory. They don't have to be. That's the beauty of it, because again, it's just a list of files in the metadata. So you could actually have, you could actually use data from existing Hive tables and just make them part of the table. They don't have to be in the structure. Like the directory structure isn't the end all be all. So now let's insert data into this table. So we're going to insert the following values. And so what's going to happen is that we're going to end up creating a new metadata file. Because again, every write, anytime you make any change to that table, if it's an update, if it's a delete, if it's a create, you're going to end up creating a new metadata file because it's a new state. And because we actually have written data, that means data files are going to get created, which means they need to be added to a manifest file that tracks those listed data files. And there needs to be a manifest list that tracks that snapshot so that they know which manifest files list the files that belong to that particular snapshot. Okay, so the metadata file is usually a JSON file. So you can see here we have two metadata files, v1, v2. So you'll see this keep going like v3, v4 as you keep making changes to the database or to the table. And then you see like the snapshot, the manifest list is saved with a file that's prefix snap. These are both, and these are going to be Avro files. The manifest will also be Avro files, and you'll see they're right there. But the data you see is partitioned by hour. So you can see it says order hour. So it knows that this is the column, and it knows that it's partitioned by hour. And then here's like the timestamp or the value. And then there's like the actual Parquet file with the actual data partition, just like you would see in a Hive table, partition in the right folder with the right value. Okay, so there we just added data. Okay, next what we're going to do is we have some additional data that we're going to want to merge into the table. Okay, so I'm going to go grab some data from this other table, merge into this table, make sure that we don't have any duplicates. Okay, so if the record doesn't exist already, then insert it. And we'll run that. And again, that creates a new metadata file. And again, each metadata file is tracking all snapshots. So you'll see like, even though this older metadata file had that snapshot and the previous snapshot, and this newer metadata file has the current snapshot, the previous one, and the previous one. And then again, the newest snapshot points to a new manifest list because it's a new snapshot, which points to the proper manifest files and the proper data files. And you can see like everything is kind of like, just keeps getting added here. Which, it does add up over time. So there are ways to manage it. Okay. So now let's say we wanted to go back in time. So again, because we have these snapshots, we can do what's called time traveling. Okay. Well, first we're just going to do a normal query. So you see here, I'm querying the table, and because I didn't specify a timestamp or do time traveling, what it's going to do, it's going to query the newest, use the newest data of the table. So it's going through the newest snapshot, which just means going through this path right here. Okay, to find the file. So basically, it's going to go let's pretend like this is like a Hive metastore. So it's going to the Hive metastore, the catalog. It finds that the current state of the table can be defined by this metadata file, which then points to this newer snapshot file, which then points to this manifest list, which then points to the proper data that it's looking for based on the query that we specified. And it never looked at this file because it knew based on the partitioning. Okay, now let's do some time travel. So in this case, we are saying, hey, I want to select all the data of the table as of this timestamp. So what it's going to do is that, again, in the metadata file, it has all the different snapshots, and there's a timestamp for when each snapshot was created. So it's going to look for, the first snapshot that's not after this point in time. So it's going to realize, hey, in this case, snapshot number 1 is a snapshot we want to look at. So instead of querying it's going to go to that manifest list, look for that has that previous list that described the table at that point in time, and again, just end up querying the files that would be part of the table at that point in time. So literally, like long as you have all these snapshots, you can go back to the very beginning of the table to any point in between and query the table as it was, which can be useful if you're trying to test like a machine learning algorithm that you did it on this data set, but you did it on the data set as it was a year ago, and now you want to run that improved version of that algorithm, but you really want to use the same exact data as it was. You could just use time traveling to make sure that you're running that against the same exact data as it was in the previous version of that algorithm. So that's pretty cool. And just to kind of show you like the numbers. So this is a case study from Ryan Blue. He's actually one of the creators of Iceberg, originally from Netflix, now with Tabular. But basically what this is Atlas was this telemetry system in Netflix that would basically track all their telemetry data. And there was a lot of data. Okay, so basically in 1 month, this system would generate 2.7 million files in 2,688 partitions. The problem is with so much data, you wouldn't really be able to access more than a few days of data at a time just because it was just so large. Okay, like the queries would take hours, if not days, sometimes to get executed. Okay, so you'd see like a query like this, where basically they're just trying to look for tags in the data. Okay, basically within a certain time frame. Now let's take a look at how this kind of query performed when it was done with Hive versus once they converted everything over to the Iceberg tables. So as a Hive table with Parquet filters, the amount of splits per day, so all these individual files that had to be looked at, over 400,000 splits per day, not combined. Okay, so just to run an explain query, so not the actual query, just an explain query to figure out what the planning would be. Okay, just that took 9.6 minutes. Okay, so just to run the explain, not to run the actual query afterwards, took 9.6 minutes. Now let's compare that to once we turn this into Iceberg. Okay, what's going to happen is that because of all that, being able to do that filtering, as we saw like in the different layers of the metadata, so we'll be able to say, okay, hey, we don't need these manifests because they're outside of our partitions. And then we take a look at those manifests, take a look at those files, and say, hey, the values in this particular data file isn't within the bounds of our particular query, and just start like eliminating all these data files. We're able to get that down quite a bit to 15,218 splits. Now what happens here, okay, the full process took 13 minutes, okay, but the planning went down from 9.6 minutes to 10 seconds, okay? And so basically the whole process, I mean, that's with the actual execution of the query, took 13 minutes, okay? While before, just to plan the query took 9.6 minutes. And now if we take advantage of the min and max filtering, okay, and take that a step further, again, that's more when you take a look at the individual files and say, hey, let's see, are these files within the bounds of the query? Then you get it down to 412 splits. Now the query planning takes a little bit longer because you're doing a little bit more filtering. But the benefit of a little extra planning, you basically end up actually it's 25 seconds. You end up lowering the total time to 42 seconds. So you went from 13 minutes to 42 seconds. Okay, so a little extra planning, a little extra 15 seconds of planning brought us down to 42 seconds. Okay, so just to kind of give you like these are like dramatic sort of improvements in speed because of the type of filtering that those metadata files really provide query engines and new ways for them to really kind of filter those files. But of course, as we mentioned, like, a thing we can do with Iceberg is compaction. So what's going to happen is that maybe you're taking in a lot of streaming data in from like a Apache Kafka server, and it's coming in as a bunch of Avro files. And the cool thing about Iceberg is that it supports Avro files. Okay, I think it's like the only one of like the three main sort of modern table formats that actually allows you to have like Avro files and ORC files along with Parquet files as the data files that make up your table. But you can be bringing in and ingesting all these small Avro files from real-time data streaming in, which again, not great for performance because you have all these little small files, the small file problem. But built into the Iceberg API is the ability to kind of do compaction, to take all those, let's say all those small little Avro files coming in from Apache Kafka, and then just rewrite them as like larger Parquet files. So that way you can improve your read times without having to affect your write times. So that data can be written real time and added to the Apache Iceberg table, and then periodically you just rewrite those data files to larger files, so that way you're optimizing your read times without necessarily without as much affecting your write times along the process. So you would just kind of schedule this like the Apache Iceberg API. One has the actual like functions and procedures to carry out compaction, but also has like a built-in event, so that way you can like trigger them, or you can rely on the events that might exist within a particular engine to trigger these events on a particular schedule or particular times. Okay. Now, this offers us a lot of benefits, this whole structure of Iceberg tables. So again, basically having this metadata tree that really stretches data and provides a lot of metadata constantly and incrementally, it's going to allow us to make smaller updates pretty efficiently. Because again, you don't need to replace a whole partition to add a small bit of data. It's just going to be a new metadata file and maybe a new data file, and that's it. Doesn't have to really change much. Okay, especially if you're making updates or deletes, it can make them pretty efficiently because it makes the changes at the file level. Now, since you have a new snapshot for every time you update the data, that snapshot isolation provides you those asset guarantees. So now you can do those updates, you can do those deletes with those asset guarantees on your data lake. Okay, I mean, we take for granted, like in your OLTP systems with like a Postgres database or a MySQL database, yes, I got asset guarantees all day and night with whatever transaction I want to do. But as we start looking with like, larger sets of data, and we're working with Hive tables, a lot of that stuff, not so easy to do anymore. But Iceberg makes that very possible, and makes it almost like just like you're using an OLTP system. You just do your transactions and it just works. Of course, there's more to it. It uses a system called like optimistic writing. So what's going to happen is that two writers come in, whichever writer writes the new snapshot first sort of wins, and then the next one will just reattempt the snapshot. Because the idea is that all the snapshots have to have like that sequence. So basically the API knows like, oh, okay, there's been a new snapshot since you were attempting to do this. So you need to try this again, factoring in the new snapshot. And that allows everything to kind of stay sequential and stay in sync. So that's how we do the concurrent writing. Okay, you get the faster planning and execution time because you can, again, first filter out big chunks of data, at the manifest list level before you filter out individual data files at the manifest level, before you start filtering out individual records when you actually scan the data files. Because you have that tree structure, you can really like efficiently plan and really like speed up reduce what you're scanning and speed up your queries quite a bit, and have really robust query planning. Okay, and then on top of that, again, as it's writing these files, like there's all these stats about the table being saved in all these files. So you're always going to have like really up-to-date stats on the table. You don't have to run these queries on the whole table to get table stats. They're in the metadata, and they're always nice and crisp. So you're going to have much more sort of consistent, up-to-date data, and it's going to be right there, and so you'll have reliable metrics on your table. Okay. because generally, again, we're generally updating that data as we write. So every time we're writing, we're updating the data that we have on the table. And we're abstracting the physical. Again, you're not dependent, you're not locked into the files being organized physically in a particular directory structure. Files can be outside of a standard directory structure. Again, like if you want to migrate your existing Hive tables, I could just sit there and say, hey, I have this Iceberg table. I want the data files from this Hive table to be part of this Iceberg table. And I can just run a migrate, which is a procedure inside of Iceberg. And all it does is just basically write a new snapshot that includes those files. And now those files will be part of the query, even though they may be off in some other directory somewhere else. So bottom line is that it gives you that flexibility. And that's going to allow things like the hidden partitioning, because again, the partitioning isn't purely based on how the files are organized. It's based on that relationship between like a possible transform and the column. So I can be like, hey, this is a timestamp column that I'm partitioning by, but I'm doing a day transform, a month transform. And on top of that, not only can I express that partition as a transform in a particular column, which means I don't have to do like a double statement. Again, that whole issue where I query the timestamp column, but then I also have to make sure I query like the additional partition column. I only have to query the timestamp column. It's going to work. But I'm also going to be able to do run compaction. But first, I want to go to evolution. So I'm just go to that. Okay, but I can do partition evolution, where if I'm partitioning by day, I can then, or if I'm partitioning by year, I can then shift the partitioning by months, and then I can shift the partitioning by days, and there's no rewrite of the table. It just tracks, like Iceberg will just track that this data here is partitioned by year, this data over here is partitioned by month, and then this data over here is partitioned by day. It's just going to be doing it on the data going forward, and that's Iceberg is the only one that can do that, and that's really cool because again, you're avoiding the rewrites. And again, people querying your table, they just query the timestamp column. They don't have to think about it. They're going to get the benefits of all those existing partitions. But you can run compaction that's built in, so you don't have to really overly think about it. You just run the compaction with really good strategies that are built in to the Iceberg API. They have multiple strategies for multiple situations, depending on how you want to do that compaction. Like, do you just want to write the files to target a certain size? Do you want to sort them while it does compaction to provide other optimizations? You can decide, how long do you want this process to take relative to sort of like how much it optimizes the data. You have all these strategies kind of built into the API. Tables can change over time. So again, you can do that partition evolution. You can do the schema evolution. So, and again, while other table formats do provide for a schema evolution, none of them provide for the full suite like Iceberg does, which is to be able to not only add tables, rename tables, change the order of tables, update the types of columns. Basically the full suite of updates you can do. Okay. And plus you can experiment with the table layout because basically everything is isolated into snapshots. So if you make a change, like you're repartitioning something and you don't like it, you can always just roll back. You can always roll back to a previous snapshot, or if data didn't come in right, you have that flexibility to roll back to previous states of the table. So mistakes aren't as painful, which is really, really nice. And then on top of it, also has, especially when you're migrating, it has some extra features like a procedure called snapshot that allow you to create like a temporary test version of an existing Hive table as an Iceberg table, so you can audit it before you actually do the migration. So there's a lot of really, really cool APIs in there. But again, rich schema evolution support. Again, very rich compared to alternatives, where basically I just put out this article comparing Apache Iceberg, Delta Lake, and Apache Hoodie, and then there's a section on the schema evolution support, and you'll see like Iceberg offers a lot more when it comes to schema evolution. And the cool thing is that again, when any engine, so if I have one engineer using Presto and another engineer using Dremio and another engineer using Spark, it doesn't matter what engine they're using. They're all connecting to the same catalog, and the catalog is going to point to that newest snapshot. So they're all going to see the same data. And if let's say someone on Spark writes some data and a new snapshot gets created, the next query that comes from like Dremio or Presto, they're going to see they're going to see that data right away. So basically, you're gonna be able to just write to the table, and everyone just sees it. Okay, it works real well that way. And again, you can latch into events to kind of trigger things like compaction, expiring snapshots, and other sort of maintenance procedures. So that's all well and good. Okay, and because it's open source, they're constantly adding new features to it. It's very plug and play because you got that exposed API, so different things can be built on it. Like I mentioned earlier, something called Project Nessie, which was built sort of with Iceberg in mind. And basically, what it does, it acts as a transactional metastore for Iceberg tables, which adds some really cool features because now you can actually have different versions of the current snapshot. So you can always have like a Git-like experience where you can say, hey, I'm going to create a branch. Hey, let me go add data, audit the data, work with the data. And then when I'm done really kind of making sure that all this new ingested data is, nice and clean, I can actually go merge it back in and merge it back into sort of like the main branch. And all my data consumers, they never need to know that I was doing all this ETL work at the time. No worrying about partial queries because all that work's being done on a branch. And when it's ready, I just merge it in and it's just like it all just magically appears one big giant multi-table, multi-user, multi-engine transaction. Because while you're on that branch, you can do transactions with multiple tables, multiple engines, multiple users can be doing it. So that kind of pluggability into other projects really allows for some really cool stuff that could be coming down the pipeline. So if you want to learn more about Apache Iceberg, you can head over to iceberg.apache.org. You can go to iceberg.apache.org/blogs. That'll take you to the official Iceberg website. If you go to dremio.com/subsurface/Apache Iceberg, you'll find you'll find basically all the content at the subsurface about Iceberg. So that's going to include all of our subsurface conference talks about Iceberg, which there's pretty much a talk on. I mean, just in this most recent subsurface, we had talks about maintaining tables, talks about the different types of compaction strategies, basically anything you can think of. Also, a lot of articles that were recently released. Like I mentioned, I put out an article on migration, an article. I have upcoming. There'll be an article on hidden partitioning. So a lot of Iceberg content coming out. So you can find all that there. And again, here, so you can find the Getting Started for Apache Iceberg's website. And also this Thursday in Chicago. So this Thursday, we're doing a meetup. The subsurface community is doing a meetup in Chicago. And one of the talks will be on Apache Iceberg, specifically focusing on the views feature and how views work in Apache Iceberg. So that'll be this Thursday, and you can actually attend that live. That'll be in Spin in Chicago. So that should be available on the subsurface community on meetup.com. But there will be free Iceberg t-shirts for anyone who attends. And I'm pretty sure they'll be giving out like free drinks and hors d'oeuvres during the thing. So it'll be fun, and you can play ping pong at Spin. So if you're not doing anything Thursday night, not a bad place to come hang out with us. But with that, that wraps up the presentation. And again, my name is Alex Merced, developer advocate here at Dremio, and my Twitter handle is AM Data Lakehouse. So AM for Alex Merced, then Data Lakehouse. So you can follow me on Twitter for any new articles on Iceberg or other related technologies. I'll be posting them there. But with that, I'll open this up for Q&A if anyone has any questions.
That really was a great talk. Actually, Jim Scott, if you guys remember Jim Scott, who's now in Michigan, worked at Spins many moons ago, and some of his compatriots are still there. So that's kind of a cool place.
Yes.
I haven't heard of subspace before. What exactly is, or subsurface? Sorry, what is exactly that about?
Subsurface is basically what we're doing is it's a community. It's like a developer community, but it's mainly focused on the data lakehouse. So basically, we organize this conference called Subsurface. So we just did, I think it's like we were doing it for twice a year for the last 2 years, and then we did one this year, and I think we're going to be going to one conference a year, and now like more frequent meetup events. But it's essentially a community where we're going to be we organize talks and content around the data lakehouse. So this is going to be mainly around technologies like Iceberg, Apache Arrow, Project Nessie, Parquet, things like that really enable that possibility of having the best of all worlds, the data lakehouse. It's more specifically the open lakehouse, where basically you have a lakehouse that's really kind of open and any tool can plug in, and you're no data like vendor lock-in or anything like that. So that's cool. So I'm part of like the tech advocacy team at Dremio, and our focus is really to build this particular community, the subsurface community, and just kind of educate people about open lakehouse adjacent technologies.
Cool. That's interesting.
Yeah, that actually brings me to a good question. You've got a competing group out of Databricks, and they're talking about the Delta Lakehouse and their Delta tables. How do you see that as a competition or as a co-competition, partnership, or how do you view Iceberg versus the Delta Lake?
Well, I mean, I always leave it to everyone's personal use case as far as deciding like, okay, what is the right table format for them. But as far as like some of the differences I think are important. One, I mean, there's the fact that like the schema evolution support is just very uniquely robust with Iceberg, which I think is really important. And I love the partitioning features of Iceberg, which don't exist with any of the other table formats, particularly the partition evolution, which is I think a fairly big deal. But overall, when it comes to like the whole platform as a whole, this is why we make like the distinction of like open lake houses. So like people can have a lake house where they may be using particular formats and they're still querying and working with the data on their data lake. But the question comes down to like, if later on I want to use other tools to do certain workloads, am I going to be able to? Because are the formats I'm using allowing me to use those tools that come out that exist now or come in the future? So when you're using a format like Apache Iceberg, that's true without a question. Like basically everyone has the full playbook when it comes to Apache Iceberg as far as how it's built, how it works, so they can build their tools to read and write to that format. With Delta Lake, while pretty much all engines can read Delta Lake tables, when it gets to the write question, it gets a little bit more selective as far as which tools allow you to write. But again, it just depends on sort of what your use cases are. And which particular services are best going to serve your use cases where that trade-off might be worth it. But we never know what tools are going to be in the future, so we always generally as a open lake house community, we advocate the ideas of keeping your lake house as open as possible, so that way you're future-proofed, because you never know what's coming around the corner, and that way you're using formats that can always continue to improve and continue to give you access to all tools, read and write.
And thank you. One of the as a ETL data load, we do a lot of data loads and all that stuff. One of the key feature I like about Iceberg is a web, right? Write, audit, publish concept. Can you elaborate a little bit on that?
Yes. Okay. So WAP, the write, audit, publish process. So this is basically a paradigm of how you would use Iceberg, let's say with a tool like Project Nessie. And basically the idea is this: like you can write the data, and instead of writing the data, like right now, let's say you write the data in the current paradigm, you might just write the data to your Hive tables, and now you still haven't had a chance to do your auditing and quality control work, and you're worried, hey, someone might have queried the data with with some unclean data. But when you mix Iceberg and Nessie together, what I can do is I can ingest that data on a branch. So I can sit there and say, hey, like these ingestion of streaming jobs, I can set up Flink to ingest those onto a branch instead of directly on the main branch where all my data consumers are querying. And that data is coming in there. I get to sleep at night. I can sleep at night knowing that no one's querying bad data. And then I can go run my audits. I can go double check for referential integrity, check to see if there's any missing data, just do all my checks. And once I feel like everything is nice and good, that's when I can do the publish part. And then I just do a merge, and all that data just magically suddenly becomes available to my data consumers. And it's not like I'm doing it incrementally where people can accidentally query those incremental changes because I did it on that separate branch.
Yeah, thank you. I think it's going towards data as code, right? Concept. Right?
That's right. Yeah, basically it's going to be like a developer experience where you just kind of like a Git with code, or that data as code type experience is what sort of that combination of Iceberg and Nessie can provide.
And also I can do zero copy cloning with the branches, and then I can test it, and then I can do all kind of stuff. Or you
Correct.
can go ahead. Yeah.
Oh yeah, that's 100% correct. Thank you. Because basically what happens is that when you're using Nessie, so and again, just to kind of go back a step with how Nessie works, is that it's basically in the same way that the catalog tracks that newest metadata pointer. Instead of just tracking one metadata pointer, it can actually track the branch's current updated metadata pointer, and then be like, okay, well, so only thing you're really making only additional files are additional metadata files, but they're all working from the same data files. So then when you make that merge, all you're doing is creating a new snapshot on the main branch, and you're just basically you're not duplicating your data. So it's not like other offerings where you're creating that try to give you version control, but what you're actually doing is creating a duplication of all your data when you create those alternative branches. You're only creating a branch of your metadata, not of your data.
Thank you. So when is the NESI general availability coming in?
Well, I mean, NESI is available now. Anyone could technically implement NESI now, far as just setting up a NESI server that they can work out of. Now, if they want to use it in a way that's managed for them, of course, there is Dremio's Arctic service, which is basically a managed NESI server. So that way you can take advantage of those features without having to do any of the work. And there's gonna be some cool features coming down the road. I don't want to get too far down that road, but that'll go. Right now it's in public preview, and we'll go GA when it goes GA, which should be this year. But there's some other really cool features that are gonna be tied up, and I don't want to release say too much.
Okay. So I'm going to actually stop the recording now. Again, Alex, thank you very much for the presentation. It's very good. I'm going to hopefully get this posted. We haven't figured out where, and when we do post it online, the recording, I'll send out a message to everybody in CHUG. So we're going to stop.